By the way, there's several of y'all who are using Macs. If y'all could get together and help each other on this, it would be cool.
I can have a bonfire this week and you guys can...
That would work. No, that's probably not what most of them want to do, but you could check. So what we're going to talk about, and turn the lights down a little too much today. I guess I could write here. Bits and bytes. A bit is the smallest unit of information that you could pretty much have. It's either a 0 or a 1. And why is it chosen? Because an electrical signal can either be off or it can be on. Now in the 1950s and the 1960s, there was a Soviet computer manufacturer that actually made what are known as trinary computers, where each bit could contain one of 3 different values rather than 2. And that was a bizarre beast, and they stopped making those, and nobody's done that since because there's no point to it. So a single bit is not very useful. Information in your computer is clustered in groups of bits called bytes. Eight bytes to a bit. And that is arbitrary. There was no, fundamental law that said that a byte had to be 8 bits. It could have been 12, it could have been 16, it could have been 4, it could have been 7. It's just that at that time when computer architecture was being solidified and somebody came up with a name in the 60s, they went with 8 because that was the current state of the art. And it is stuck. Even though computers now use longer groups of bits to shuttle around, your PlayStation or whatever may be sending 64 bits at a time rather than 8 when it's doing processing, or 128 or whatever, rather than just 8. The nomenclature has stuck.
Isn't it 8 bits to 1 byte?
Yeah, it is.
8 bytes to a bit is what's...
Thank you for correcting me.
You're welcome, sir.
8 bits to a byte. And the guy who named them made a conscious decision not to call it a byte with a capital I, just because then it would be more easy to confuse when you were looking at it. So we've got our Y, the long sound meaning the larger size. Okay, so here's a byte. We have 8 here. The minimum value that a byte could store would be all zeros. And the maximum value would be if they were all 1s. And as far as we are concerned, it doesn't matter how that is stored. Whether those are vacuum tubes that are lit up, or whether they're, AND gates on a solid state RAM disk, or whether they're spots on a magnetic disk, or, pits on an aluminum disk for a CD or whatever. All we need to know is that they're clustered in groups of 8. And for most of today, I'm actually going to be talking about groups of 4, just because the math is easier if we do groups of 4. So let's learn to count. Now this is not supposed to be pedantic, but sometimes when people see counting in binary, it kind of bugs them. And if we can put it in context of counting in decimal, which is base 10, it makes a little bit more sense. So say we had a car, it's got an odometer, and we're going past a certain number of miles. So on. So, brand new car starts off with 0. We pass the first mile marker, that rolls up to a 1. We pass the second one, the third one, that rolls up to a 2 and a 3. 4, 5, 6, each mile. 7, 8, 9, 9. Now we hit the 10. Now what are we going to do? Our numbering system starts at 0 and has 10 digits in it. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We can't increment that one anymore. And you all know what the odometer is going to do, right? It rolls over so that that's a 0 and then that becomes a 1. And then we continue iterating the ones place. 11, 12, 13, 14. We've hit our destination. And the odometer reads 14. Yay, we've learned to count. Okay, so what are these places really? We call this the tens place, the hundreds place, the thousands place, and the ones place. In reality, what it is it's 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. Any number to the power of 0, or any positive number to the power of 0, is 1. Mathematically, I don't understand why, but that's true. So 10 to the power of 0 is in fact a 1. And you know what I mean when I say power. Like a number to the power of 2 is that number times itself, a square number. And a number to the power of 3 is that number times itself 3 times. So 10 to the 1 is a 10. 10 to the 2 is 100. 10 to the 3 is 1,000. And those are our places. And if we had, more of them, we would have 10 to the 4, 10 to the 5, 10 to the 6. Another way of thinking about it is that the 0 specifies, or the power specifies the number of zeros after the 1. 10 to the power of 0 doesn't have any zeros. 10 to the power of 1 has 1 0. 10 to the power of 2 has 2. 10 to the power of 3 has 3 zeros. That is in base 10. Now we're going to do base 2. So we have an odometer over here, and it also has 4 digits. It's in base 2, it's in binary. Base 10 is known as decimal. Des meaning 10, like a decade. Base 2, it's called binary. All right, so we start off as 0. Now binary doesn't have 10 digits, it only has 2. It only has zeros and ones. So we hit the first mile marker, we go to a 1. We hit the second mile marker. What do? We've already maxed this one out. We can't go past 1. So what are we going to do? Yeah, that rolls back to a 0, and that becomes a 1. And I'm sorry, I had my back to you, so I didn't lose.
Oh, no, you're cool. I was just going to say, one of the biggest reasons why computers operate in binary is because it's also because hypothetical computers before we had digital processing, usually the math was done in binary as well before they had it done in electricity, so like mechanical computers.
Right, because you had mechanical relays that could be off and on. Or, it's a simple way of thinking about things.
Asimov and specific.
So, okay, so once we got, I'm going to put little numbers here, but they're going to be decimal numbers. Once we got to that marker, 2, we had to roll that one back to 0, and we put a 1 there. All right, then we hit mile marker. Another 1. All right, now we hit 4. What's going to happen? Can we stick it there? No. Can we put it there? No. So these are all going to have to roll over, and that's going to become a 1. All right, so we're going to hit 5, 6. Well, that one's already a 1, so that has to flip back to 0, and that one rolls over to a 1. 7, 8, 9, 10, 7. 8, well, we've already got these all flipped to 1. We can't make any more, so they all roll back to 0, like the rolling over the odometer. I was always really excited. Ooh, I hit 100,000. Okay, so we have, a 1 followed by 3 zeros. 9, we get to change one of them back to a 1. 10, that flips back to a 0, and that flips to a 1. 11. 11, 12, 13, 14. I don't know. Eventually we wind up with 14, which is 1110. I hope that's right. Yeah. Okay, so I'm going to lower the screen for a moment, and we're actually going to count out the numbers on the Word document. So base 2 has 2 digits, 0 or 1. Base 10 has 10 digits, 0 through 9, also known as binary. And when I write base 2 numbers, I will often indicate them with a closed parentheses followed by the number 2. And if I'm being really cool, I would even make that a subscript. So base 10 is also known as decimal. Same thing. If I'm writing a base 10 number and I want you to know that it's base 10, if there's any confusion about that, then I would specify it like that. with a parentheses followed by the 10. So, you know, examples of a base 2 number could be 0, 0, 0, 0. I want them larger than that. And then I would put that to indicate that it was base 2. Or maybe 1, 1, 1, 1. I thought I told you to stop subscripting there. I'm just going to copy and paste this. You know, some number in between those, like 0, 1, 0, 1, and so on. So let's count. 0, 0, 0, 0. Whoops. Back into this. That's the smallest one. And then we start going. 1. Then we flip the next one because if 1's place rolls back to 0. Now we have 1, 1. And I know this is pedantic, but we will make use of this later. Okay. 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. I'm going to stop there. We're going to leave the last bit 0 because I don't feel like doing 8 more of those. So here we go. This is the number 0 in base 10. This is the number 1. This is the number 2. This is the number 3. This is the number 4, 5, 6, and 7. Now, do you need to memorize that a 7 is 3 1s and a 5 is a 1, 0, 1, and so on? No, you don't. You can use the powers of. Just like we wrote the powers of 10, we're going to use powers of 2. So we have our 4 spots. This is 2 to the power of 0, which again, any number to the power of 0, as long as it's not 0, I believe is 1. 2 to the power of 1 is a 2. 2 to the power of 2 is a 4, 2 squared. 2 to the power of 3 is an 8. If we had more bits, it would be 16, 32, 64, and 128 if we were going all the way out to a byte. But like I said, for most of this, we're just going to deal with 4. So if we have some number here, like 1, 0, 1, 0, we can figure out what it is. Because this is 1 times 8, because that one's lit up, plus 1 times 2. So we have 8 plus 2 is 10. So 1, 0, 1, 0 is 10. Let's put another number in there. Let's put in 0, 1, 0, 1. Now we're lighting up the other ones. So this is 1 times 4 plus 1 times 1. So that's 4 plus 1 is equal to 5. And I'm realizing now that I skipped something why I'm doing these times. I'm sure you already know, but let me raise this back up. So in our decimal counter, if we had the number 2016, what this really means is 2 times 1,000 plus 0 times 100 plus 1 times 10 plus 6 times 1. So, you know, that matches that. That matches that. That's really 0 times 100, you know. That matches that, and that matches that. And these numbers indicate, are the powers. 1,000, 100, 10, 1. And sure enough, if we added all those together, we would in fact get, 2016. Same idea with binary. If we have all 1s, well, we already said what these values are. This is a 1, so what's the next one? 2, so what's the next one? 4, and so the next one's an 8. So if they're all lit up, if we have 4 bits in a row lit up, that's 8 plus 4 plus 2 plus 1 is equal to 15. So really, if you don't have a huge number of bits, if you're just looking at 4 of them, you can eyeball it and add it up really fast. What is 0111? Well, it's 1 plus 2 plus 4, which is 7. What is 1001? It's 1, skip the 2, skip the 4, plus 8, so that's 9. 1100, skip the 1, skip the 2, it's 4 plus 8. You see what I mean? So now I can give you binary numbers, and you'll be able to convert them in your mind, or on paper or whatever, to decimal.
Now let's do it in Little Endian format.
Yeah. That comment, the quasi-joke, is based on the fact that some computer manufacturers decided that when you had a large number, I'm going to do it like this, but this is not strictly true because it wasn't that numbers that small. Did you store the high order part of the number first, or did you store the small order number first when you were writing it out, you know, to hard drive or something like that? So if you opened up your hard drive and you looked at the bits, would you see the numbers 97, or would you see the numbers 79 written out? Intel chose Little Endian, which means that if you looked actually down deep inside, the numbers look reversed. 79 rather than 97. And again, they're not that small. They're larger clusters of numbers than that, but that's the idea. So a big Endian one is one that writes the numbers out to memory in the order that you would expect, the high order ones to the left and the small order ones to the right, whereas Intel did Little Endian, small ones first and then the large ones. That really doesn't make any difference to us as programmers, but if you were writing something that needed to read direct memory, you know, from something else, you would have to make sure you knew which one you were doing. So Unix developers, you know, half of them were writing for Motorola chips, which were Big Endian, and half of them were writing for Intel, which were Little Endian, and they wanted to make sure that when they read that data, they knew which format, you know, they were reading from. Okay, so why don't we go ahead and do the next 8? So I'm going to go ahead and put all these out. But it's pretty easy because I just grab this whole shebang here, paste them, and now we go 8, 9, 10, 11, 12, 13, 14, and 15. Now if I had lined these up side by side, we would see that an 8 is about the same thing as a 0, except it's got the 8-bit turned on. And so in order to get all these ones after 8 to work, I just flip that first bit. There we go. And we can eyeball it. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. So that's true. 1 plus 2 is 3, skip the 4, plus 8 is 11. So looks good. I will go back and I will format these notes to be much prettier. But I'm making these up as we go along so that we do have a record of them, as well as the video that we're recording. Unfortunately, the video does not show everything that we write on the screen. It only shows what I type. Okay, so that's one numbering scheme. I'm not going to ask you to convert from decimal back to binary because it's kind of an annoying process. There's 2 ways of doing it. One is, well, I'm just not going to ask you, but I certainly feel justified in asking you to convert, you know, numbers like 1011 in base 2 to something in base 10. And yeah, you could just scroll back up here and look, but don't do that. Actually show some work. You know, or 0110 is equal to what? Or 1101 is equal to what? 0000 is equal to what? And 1, whoopsie, Thank you so much. All right, and 1111 is equal to what? So that'll be a homework assignment. I'll upload that. It's not all of it. We're not done with the lecture. But you see how to do it. If I was going to pick one of these arbitrarily, what is that first place right there?
1.
Everybody agree? Because it's right. So we have 1. What's that one?
2.
But there's nothing there, so we're going to skip that. So we still have 1. What's that one?
It's 4.
We do have a 4, so how many total do we have so far?
5.
Yep. And then we're going to tack on the 8. So 8 plus 5 is 13. And if we go back up here, yeah, sure enough it is. So there's another numbering nomenclature that is used in computers. And it's not just designed to be annoying. It actually serves some purpose, which is known as hexadecimal. So decimal had 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Binary had 2 digits, either 0 or 1. Hexadecimal, as you can guess, there's both the 6 in there and the word 10 in there, has 16 digits. Well, how do we get 16 digits out of it? I know that half of y'all know. What do we do once we get to 9?
Alphabet.
Yep, alphabet. A, B, C, D, E, and F. And you go, what? But it makes sense. We will start counting in hexadecimal in just a moment. So let me tab this over correctly. Oh, that's going to be annoying. So anyways, that means that that would be a 10 if we were counting in decimal. And that would be 11 if we were counting in decimal. That would be 12, 13, 14, and 15. Then once you hit 16, you roll over. So let's count in hex. We're only going to do 2 digits. That's 0, that's 1, that's 2, that's what? That's 0, that's 1, that's 2, that's 3, 4, 5, 6, 7, 8, 9. But now we're counting hex, so we're not going to flip it to 1, 0 yet. What is it?
A 0?
Yeah, 0A.
Oh, 0A.
0B, 0C, 0D, 0E, and then 0F. Now we have exceeded the capacity. You know, we have 16 different digits. We've used them all. So if we want to tack one more onto it, then we reset this one back to 0 and we go to 10. And if we counted these out, then that's a 0 in decimal. Let's see, so this is base 16. This is base 10. So that's 0, that's a 1, that's a 2, that's a 3, that's a 4, 5, 6, 7, 8. That's a 9. That's 10 in decimal, 11, 12, 13, 14, 15. And it's not until you get to the next one that it's 16. Okay, so if you're going to put those in some kind of format like this with powers of, you do the same thing except it's going to be 16 to the power of 0, and 16 to the power of 1, and 16 to the power of 2, 16 to the power of 3. And I'm not going to do too much with hexadecimal, but I'm going to show you why it was considered useful. So we have, let's say, 4 digits of hex. This would be 16 to the power of 0, which is the 1's place. 16 to the power of 1, which is the 16's place. 16 to the power of 2, which is 256. And 16 to the power of 3, which is 4,096. You know, 16 times 16 times 16 is 4,096. So if we had this number in hex, 3,301F, we could figure out its decimal value the same way we were doing that binary stuff. This is 3 times 4096, which I can't do in my head, so I shouldn't have made it so large.
12,288.
Thanks. Plus no times 256, plus 1 times 16, plus, and what did we say an F was? 15, so 15 times 1. We could add all those up and we would get our answer in decimal.
12,305.
And you could get online and find hex to decimal conversions. The Windows calculator even has it in there. But if I did ask you to convert it, I would want you to show your work. But I'm not going to ask you to convert hexadecimal to decimal. I just want you to see the process so that you're thinking in those terms. Kind of interesting that the largest value in 4 digits of hex is equal to a pretty large value in decimal, 65535. Why is that possible? Well, because you have more information per digit, because each digit is one of 16 different choices rather than 10. So why is that cool? Well, what if we had an area of memory which was all ones and zeros, as memory is wont to be, and then we wanted to be able to display it on the screen in some fashion that made sense. So 1011, 0001, 0000, 1000. Okay, that's 4. I'm going to go out to 0110, 1010, 0011, 1001. I think I have 8 now. 1, 2, 3, 4, 5, 6, 7, 8. Looking at that on a screen, your eyes would roll up, especially if there were no spaces in it, you know. You would not be able to make heads or tails of what all that was. And yeah, you sometimes would want to be able to browse through the contents of your memory and look just at the pure values. You know, if something has gone wrong, if you've got a file transfer and something is wrong and it's corrupted in some fashion, you may need to open that file up with some kind of viewer that would show you the raw contents of the file. Displaying the raw contents in zeros and ones would make your eyes roll up. You know, if this was an MP3 header or a JPEG header or a PNG header or something like that and it was all ones and zeros, you couldn't make sense. You would have to turn it into something that made more sense. Well, let's turn them into decimal. What is 1001? Well, that's a 1, that's an 8, so that's a 9. What is this one? What is that one? What is that one? What is that one? 1. That one? It's a 1 plus a 2 plus an 8. 11. What is that one? If I could write it clearly. 5. Yeah, 6. And this one is a 2 plus an 8 is a 10. Okay. So with this scheme, if we were converting each, now this is really silly, but a half a byte is known as a nibble. Sorry, I didn't make it up. Half a byte is a nibble. Each nibble being represented by a decimal number takes 2 spots. Not necessarily, you know. That one looks like it only takes 1. That one only looks like it takes 1. But we had several places where it took 2 to represent a nibble. And the reason for that is because 4 bits can equal any value from 0 to 15. So on a screen or on a printout, when you were displaying this, you would have to display it like this. 10, 16, 11, 01, 00, 08, 03, and 09. Yeah, that's useful. You know, you would be able to make some good knowledge out of that. But if you had an 80-column screen and you wanted to maximize this, if each one is taking up 2 spots to display, you would only be able to display 40 pairs of numbers, which means that you would be displaying 40 nibbles, which means that you would be displaying 20 bytes per one line on your line printer or one line on your screen. But if you convert them to hexadecimal, it's much better. Let's make our little chart here. We're going to make a little table here, an 8x6 table. Not 8x8, but oh well. So this is going to be the decimal, this is going to be the binary, or the hex. Hexadecimal is also just some sometimes shortly called hex, and this is going to be the binary. And we're going to repeat that over here, decimal, hex, binary. And we're just going to count them down again. 0, 1, 2, 3, 4, 5, 6, 7, 8. No, 8's going to be up here. 8, 9, 10, 11, 12, 13, 14, and 15. So hex is going to be the same until you get to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. What is this? A, B, C, D, E, and F. And then the binary versions. 0, 0, 0, 0, 0, 0, 0, 1. I'm not going to read them all out. If you look at this, you can kind of see some patterns to it. When you're counting in binary, the last bit always flips every time you go up. So if it ends in a 0, you know it's an even number. If it ends in an odd, it's an odd number. And then the second to the last bit bumps every 2. Here it's a 0, here it's a 0, here it's a 1, here it's a 1, here it's a 0, here it's a 0, here it's a 1, here it's a 1. The third to the last one bumps every 4. 0, 0, 0, 0, 1, 1, 1, 1. The fourth one bumps every 8, which is why it's 0 all the way down here. But then when we do it over here, it's going to be the same numbers, just with that first one set to 1. So an 8, 9, a 10, an 11, 12, 13, a 14, and a 15. And we could eyeball it. Let's just make sure. 1, 0, 1, 1, that's a 1 plus a 2, which is 3, plus an 8, which is 11. Don't know where my brain was. And yeah, it is 11. Okay, so we have a cute little chart here, which allows us to convert binary to hex without doing any intermediate steps. You know, you don't have to convert from binary to decimal and to hex if you have these numbers memorized, or if you're looking at this chart. And believe me, if you were a programmer who was staring at these things, you know, within a couple of days, you would certainly have them all memorized. So here's our nibbles. Tell me what 1010 is in hex. That's an A. What is this one? What is that? We're kind of cheating because I could just look and I know that an 11 is a B. So what is 0001? That's a 1. All zeros is a 0. 1000 is an 8. 0011 is a 3, and 1001 is a 9. Okay, I didn't throw in enough letters. You know, if this had been 1111, that would have been a little more interesting because that would have been a 15, and that would have been an F. So when we wrote out our numbers over here, that one would have been a 15. So we wrote it out in decimal here, but now we can write it out like this. A, 6, B, 1, O, 8, 3, F. Each nibble only takes one space, one character of your display, rather than 2, as it did with decimal. Decimal, it took 2 per nibble. Here, in base 16, it took 1. So in an 80-column display, you could display 80 nibbles, or 40 bytes, in hex, which is cooler. You can see more on the screen at the same time. Here, this is kind of redundant because this first digit never gets past 1. It's always either a 0 or 1, and most of the time, it's a 0. So, you know, why would you want to display it in decimal if you could look at it in numbers and letters form like that? Let me give you an example. It's called a hex dump. A hex dump is when you're looking at memory and the bits have all been converted to hexadecimal for display. Here we go. Now here they've tidied it up a little bit by putting spaces. But each one of these is a nibbles, so that's 4 nibbles. 4 nibbles is 2 bytes. That's 2 bytes there. That's 2 bytes there. 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 And by looking through this, if you knew what you were looking for, you'd be able to see some patterns. You know, if you were told that at position 70, there was going to be a number there, and you knew that you were dealing with Intel and you were dealing with little endian, then you go, okay, I'm expecting to see the number 57 followed by 00, and okay, they're swapped, and that's cool. You know, this would make sense to you.
It's the far left. Is that the memory address?
Right, right. Starting at 0, and then at 10, which is really 16 in decimal because this is also counting in hex, and then 20, which is really 32, and then at 30, which is really 48, all the way down to here, which is really 256. So MP3 header. All right, if you're a fan of the, this isn't the one that said the dead milkman. Anyways, so this is looking at the header of an MP3 file. It's not as much fun as the one that I pulled up last time. But files like this tend to have some header information in them, which indicate what type of file they are, and then some information about the file. And I'll find a better version of that. If you look up a JPEG format, for example, you will see that all JPEGs start with a certain set of characters. They all have JFIF in that position. That indicates that it's a JPEG, and this probably indicates it as well. There's some information here, and then there'll be some additional fields which indicate stuff, whatever that stuff is, the palette that is used, how many colors are in the JPEG, the length of the file, that kind of stuff. This file was created by an Adobe program, and the user's name was Ducky. I don't know. So I want to find that better version of the MP3 header that I had. Is that the same bit? Wrong one. Thank God. What'd I do with it? See if I saved it. All right, forget it. Taking a little too long to find. I think I've... Nope. Here we go. Alrighty, a dump of somebody's dead milkman track. Weren't the dead milkmen a Norman group? I don't remember. Anyways, so the specific position in the MP3 file, you have to store the name of the artist, or else you wouldn't be able to display it on your player. You'd have to be able to display the name of the song. What kind of track it is, alternative. You know, what it was compressed with, audio grabber 1.83, lame, you know. So all of this information is useful stuff. If you were a developer of a musical, you know, player, you would want to be able to display an MP3 file, and if it wouldn't play for some reason, you'd want to be able to bring up the file in a hex editor and go and look at the individual tags, and I'm sure they have more specialized, you know, programs for displaying all the tags. But that's the idea, and you see, you know, hex, just like we were looking at over here, but then also what's known as the ASCII representation of that hex. And we haven't talked about ASCII yet. So that's going to be the last thing that we talk about here. Almost. We did some conversion from binary to hex. Now we're going to go the other way. We're going to convert hexadecimal to binary. So I'm just going to write some letters, and then we're going to turn them into bits. 1, 0, B, C, D, E, A, F. Why did I choose that? Just to be goofy. Okay, So in bitwise, looking at our chart again, which you would very quickly have memorized, like I said, not that chart. What is a 1? What are the 4 bits for a 1? 0, 0, 0, 1. I know what a 0 is. 0, 0, 0, 0. What's a B? 1, 1, 0, 0. No? That's looking wrong. 1, 0, 1, 1, and then what's a C? That is 11. You're saying the decimal version, and I'm asking for the bits. So when I needed to look up a C, I was hoping for that. All right, so what's a D? 1101. What's an E? 1110. What's an A? 1010. And an F I happen to have memorized, it's 1111. Okay, so it was pretty easy to take this hexadecimal number and convert it straight into bits. And we know how to do it in reverse too. So if I have 0111, 1010, and I ask for the hexadecimal representation of it, that's a 7. What's the 1010? That's an A? Yeah, okay. There we go. I will be very specific when I say what to convert to. You were converting it to decimal, but I would have said, you know, go from binary to hex. So let's add those on to the homework problems. And as I said, I will expand this. So let's convert DAD 7011 into binary. So a D is a 1101, and E is a 1110, and A is a 1010, and a D is a 1101, and then a 7 is an 0111, and a 0 is a 0000, and a 1 is a 0001, 0001. And I could tab these out nicely, you know. Put it in a little table, which I will do on my own time. Or we can go in reverse. If I give you 1111, 1001, 0110, 1011, you know, convert that to hexadecimal. Well, that's an F. What's 1001? That's a 9. What's 0110? 6. And this is 1011, which is a B. So convert binary to hex, and there we go. So for homework assignments, convert the following sequences to hex: 1101, 0110, 1010, 0101, 0000, 1111, and then convert the following hex sequence to binary. A, B, D, 7, A, O, F. Nah. F, O, whatever. Okay, there we go. So we have 2 sets of homework problems in here, and I will format this more clearly. Here's,
So you're putting this all on D2L?
yeah, this will go into D2L.
Are we doing it in a Dropbox?
You can, it'll be in a Word document. You can just modify the Word document and upload it again. All right, since we have a few minutes left, we're going to talk about ASCII and its representation. ASCII is a character set because, you know, pure numbers, how could we store the word, you know, rows if all we had were, you know, hexadecimal? We couldn't, you know, R's and O's and S's and, you know. doesn't work. So you need a representation that can convert text into some kind of numeric format so that it can be saved to disk or transmitted over a wire or something like that. And the format that was come up with, there were two rival formats, an ASCII won out. Looks like this. Helps if I can spell. So the beginning of it is all this gobbledygook called control codes, which we pretty much don't care about, you know. End of transmission, start of text, end of text. This is stuff that's pretty obsolete. You don't see that used anywhere. You do see a couple of them. Line feed and form feed and carriage return. A form feed means new page. Carriage return means that you hit the enter key. Line feed means that it went to the next line. In some operating systems, it's assumed that if you have a carriage return that you also do a line feed and it goes to the next line. In other operating systems, it's expected that you write out both of them, that you write out a carriage return and then a line feed. So if you're looking at a hex dump of that kind of file, you would see 0Ds followed by 0As. Then the text, if you were going to write rows state, those are over here. So like an R is a decimal 82, and an O is a decimal 79, and an S is a 83, and an E is a 68. So we could use this chart in order to encode some text into hexadecimal. And then if we were nuts, we could convert that into binary, but we're not nuts. So let's do that. Let's take the word rows followed by a carriage return because they hit the enter key line feed. DOS and Windows expected those to be in pairs, but I think Unix just accepts that if you have a carriage return that it implies a line feed. I may have that backwards. And then rows state followed by another carriage return and another line feed. So looking up there, tell me what an R is in hex.
52.
52? Okay, what's an O?
All caps.
Yeah, all caps.
4F.
4F, what's an S?
Is
53. What's an E?
45.
45. What's a CR? That's a 0D. What's an LF? That's a 0A. These are over here. Carriage return is a D. And a line feed is a 0A. Okay, so now we're back to S. S, I think we said, was a 53.
Yep.
And a T would be one more than that, is 54. I only hear one person talking. Y'all know how we're doing this? Like we're looking up R and then we're going to the hex column, which is the red column. So if we were doing a Z, that would be a 5A. If we were doing W, that would be a 5-7. Onward and upward. What's an A?
41.
41. What's a T? We've done that one. That's a 54. What's an E?
45.
45. And then another carriage return and line feed. Carriage return being a 0D and a line feed being a 0A. So if I wrote the word rows enter, state enter in Notepad and saved it as .text, and then I had a hex viewer and I looked at the file, I would see something very similar to that. This is how it's encoded when it goes onto the hard drive. And of course that's not strictly how it's encoded. You know, really 52 is a pair of nibbles that we would convert to binary. And 4F is another byte that we would convert to binary. And 53 is binary, you know. But that's the idea. I'm not going to ask you all to convert ASCII to hex. But I want you to have the idea. Now, obviously, ASCII is not really adequate for modern communications. It was great for the Americans and for English. They designed it so that it, you know, held every English character, A through Z and A through Z, and enough punctuation. But then what if you were German and you needed umlauts and other diacritical marks? And then what if you were Russian, you know, and you had all those upside down Y's and N's and backwards R's? And what if you were Japanese and, you know, you had approximately 400 other symbols that you needed to insert in this? You could not fit those within 256 characters, much less 127. So another scheme was invented called Unicode. which has, it's a multi-byte character set. This all fits within a single byte. All the values are between 0 and 255. It's even less than that, actually. Every character could be represented in 1 byte. But if you wanted to use any of those other languages, then you need some other character encoding scheme. And Unicode does, all the languages of the earth that have been put into it. And I wouldn't be surprised if Klingon or Elvish are put in there as well. But it requires more than 1 byte per character in order to encode those. But for legacy purposes, the first 127 characters of Unicode are the same as the first 127 characters of ASCII. Alrighty, each time I give this speech, I go through it more quickly. This was more than an hour and 15 minutes the first time I gave it. It's 51 minutes this time. Let me see if I'm missing anything.
Tell us a bedtime story about Alan Turing.
Isn't there a really cool movie about him that's been released recently?
It wasn't that great.
Wasn't great.
I thought it was good.
Didn't like it? I can't stand dramatizations of people's lives.
Oh, yeah.
I like it a lot more if they do their homework, but yeah.
You like proper documentaries better?
I like nonfiction books and Wikipedia articles. Not during presidential elections that get edited every 5 minutes either.
Yeah.
Automatically.
Somebody went through, and I forget if it was Kevin Bacon or it was somebody else, but they changed his Wikipedia so that everything that was in the past tense was written instead in the future tense. And of course that got undone immediately, but people did take screenshots and circulate them around for, Giggle values.
It adds empty text in the bottom so that it's a perfect collision for the checksum of the previous article.
On the internet, within like 5 hops, we all know that person.
Yeah. Okay, so one more thing we could talk about would be the idea of a cipher. The idea of a cipher is where you are substituting values for other values in order to make a message unreadable to anybody who doesn't know the cipher. In other words, a code. So you could come up with some little chart to try to make the cipher hard. That was essentially random. You would have the letters A, B, C, D, E, F, G, and H. And then you would arbitrarily randomly assign them. So that's an A, and that's a B, and that's a C, and that's a D, and that's an E, and that's an F, and that's a G, and that's an H. So if we had the word bad feed cab in English, and we wanted to apply a cipher to it. Well, we go, okay, that's a D, that's a C, that's a B, an F is an E, an E is an H, a D is a B, a C is an F, an A is a C, and this is supposed to be a B even though you can't tell, and so that's a D. So that's an encoded version of it. That's an enciphered version of it. And then, you're the Roman messenger, you carry this messenger, and Caesar happens to have, the decrypting cipher. He could take it back. What's a D? It's a B. What's a C? A C is an A.
I thought Caesarean was just a shift cipher.
You're right. I'm going to get
sorry.
there. I'm going to get there. You got it exactly right. What's a B? It's a D. You can see that these are matching up. But doing that, coming up with 2 different tables with it randomly, that would be more sophisticated than what they actually used, which is just that they shifted everything.
You're skipping to 1940, right?
Yeah. No, not quite that complex. Those Enigma machines were awesome. But anyways, so shift everything either to the left or to the right. I'm going to shift everything to the right. So that's an A. that's a B, that's a C, that's a D, that's an E, that's an F, that's a G, and that's an H. That's shifted 1. Or we could shift it 2. That's an A, that's a B, C, D, E, F, G, and H. So if we had the word bad, head, and we're shifting it just once, well, that's a C, that's a B, that's an E, and H is a,
G.
I've confused myself. Yeah, I should have gone the other way. Shifting at 1, a B is actually an A. An A is an H. A D is a B, is a C. An H is a G, an E is a D, an A is an H, and then a D is a C. That's shifted 1. If we were going to do the shift 2, then the B becomes an H, the A becomes a G, the D becomes a B, and so on. And so all you need to know is how many it was shifted in order to decode it. If you got this message and you knew it had been decoded, encoded with a shift right of 1, then you could work backwards pretty easy. Well, I know that an A is a B. I know that an H is an A. Obviously, it would go all the way out to the end of the alphabet and not just be that, but I didn't want to write all the way out to Z. And a C is a D, and a G is an H, and a D is an E, an H is an A, and a C is a D. So you see how I'm applying this to go to something and then go back to it. And as part of this class, it'd be really easy later on when we know how to manipulate strings and pull out specific characters of them, to write a program that would do this, that would shift everything by 1 or 2 or 3 or 4, all the way out to 25 different, variations, or shift to the left by the same number. And so you could decide how you were going to encrypt your message, and then you could type in a sentence, and it would generate the enciphered version of it. Then you could write another program that was supposed to decrypt that, and you would type in your encrypted version of it, and it could display, 26 different versions of it, shifted 1 all the way over to 26, and then one of them would just leap out at you as being good English. If you wanted to get more sophisticated, you could apply some kind of rules, because in English, the letters E and the R occur more than anything else. You can apply, some kind of statistics to that to get a feel for how it should be decrypted. So that's called the Caesar cipher, I believe.
Yep.
And that would be a fun little project for a little bit later. So that you could encode messages and give them to your sweetie and tell them that they have to decode them by hand. Then tell them how to do it, and I hope it's not a breakup letter, because that'd be kind of really humiliating. Alrighty, gang. Why don't we call it a day? I can't think of anything else to lecture about in this specific turn, and my voice is about to go out. If we have any questions, we can stay and chat since we're getting out 10 minutes early or whatever. Otherwise, I will see y'all next week. I will upload this. It will be due Tuesday night at 11:59. And it'll just have the same questions that I've highlighted here in red. So that'll be up here by tonight.
So Wednesday night?
Tuesday night. Do the day before class.
Just do it when you get home.
It's due by midnight tonight. Sorry, guys. No, I'm kidding. You could do it that quickly. But, nah.
I want to write an app, pretty much row state specific, but want to organize my classes and schedule and have the Gmail and all that with it. I want to use row state's name. Who would I talk to get permission for that?
I have no idea. I will ask and find out. Are you thinking a smartphone app or a computer app?
A smartphone.
That'd be cool.
Gonna break switch.
I was when I was in like the seventh
Cool.
grade. Back when the
That'd be
TVs
slick.
were still together.
Oh, yeah.
I want to see you do that. So yeah, I'll do some asking around.
Okay. Start making. Oh, and the other one is.
Every fifth Thursday or something.
Would it?
I haven't gone.
Would I be able to like solicit a graphic design, somebody in graphic designer to
Yeah, I missed.
Might be able to. You know, I think what you would have to do is to go find out who teaches the graphic design courses and then go and ask them.
Okay. I'm not trying to sell the app to make money. I'm just-
Right, but it would be cool to, you know, have it available for free for people to use.
Yeah.
Yeah. That'd be
Eventually
slick.
turn it over to Rose State, let them maintain it.
Let them maintain it, yeah. And then they'd have to hire you to make changes to it, because they wouldn't know how. There was an iOS programming course offered one semester. I wish it was offered, you know, on a regular basis, because that would be cool.
Like encrypted?
I like it, it's kinda easy. I tried doing, Android,
Oh, okay.
it's a little more in
Did I
depth.
say
Yeah.
memorize or did I say no? Yeah,
The-
You said memorized.
okay, sorry, yeah. What
With
were
the,
you saying?
I don't know if you've messed with Swift, but
I have not, but I need to.
they kind of
I have
made
most of,
Objective-C a
like,
lot
the
easier.
16
That's
grades.
good, because it needed it. Because that I have looked at, I just have not looked at Swift yet.
Yeah.
Well, cool, I will ask, and so I should have more information the next time we talk.
He brought in,
Okay.
Sure.
Sure.
He built like 3 or 4 miners, 2 were net tops with nice graphic cards
Yeah.
that he had,
Alright,
he had
see you
been
next
running with his parents
See ya.
watching movies on them, so it was a home theater. And so because of that, he made his parents pay for his computers by providing electricity for when they weren't watching movies. So ran in the background. He made like 70 grand off of that in 3 years.
Damn.
And then he used 12 grand of that to build like a beast. It had, I don't remember what graphics cards he had in it, but it was about the highest end you could get with anything available consumer end. Like he had one of the first like consumer end computers with a PGA 2011 processor or a socket.
Oh, yeah.
I think so. It was really nice. It was really nice. Like that dude, he owns a business now, just building custom gaming computers for people. And I did a lot of coding with like the Exchange APIs. I would convert from PHP to JavaScript, and then make automated like monitoring tools and trading tools with those, or I just give people the libraries that I wrote in JavaScript so that they could run them from their cell phones instead of having to have a server running. And I did a little bit with like machine learning in relation to the cryptocurrency exchanges, and I improved a couple of money
Professor, you said the
algorithms,
homework is
statistics and
Jose-
probability,
Yes, sir.
hence knowing
Yeah.
how to do
On
the
D2?
statistics on paper.
It'll be on D2L, correct?
And then,
Yes, sir. Sure
I
thing.
do a little bit with like safety of like addresses and yeah. So one of the guys that works with us, he has a degree in math with an emphasis in statistics and
Oh, okay,
probability. So it helps when all brute forcing is based on statistics and probability.
Good person to bounce ideas off of.
Yeah. Well, a lot of the time you have to explain math to him because he doesn't know cryptography at all. He'll look at something and then he'll start.
math and computer science.
Hey, thanks for recording a video of your.
Oh, absolutely, I'll upload it.
I appreciate when professors do that.
You explained it
Happy.
1,000 times better than when I learned how to translate binary, because the guy that told me I had to look it up after figured out, like you explain it